You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Dirk Schulze-Makuch. Dr. Schulze-Makuch is a renowned astrobiologist and professor at the Technical University of Berlin. His research focuses on the potential for life beyond Earth, planetary habitability, and the conditions under which life might thrive in extreme environments. He has authored numerous scientific papers and books, including works on life in the solar system and beyond. His interdisciplinary approach combines planetary science, biology, and chemistry, making him a leading voice in the search for extraterrestrial life.
Dr. Dirk Schulze-Makuch, welcome to the program.
Thank you for having me.
Now, Doctor, Mars seems to be hinting in some ways that there may be an environment still capable of supporting some level of life, especially subsurface and in briny water. And I know you've been doing work on that. And that we see places very similar to this, the Atacama Desert, where there is still life there. So if you had to bet, you think Mars is, you think we should be looking for microbes before we ever put human boots on Mars?
I think so. There's several reasons why we should do so. We really have to start with Mars like 4 billion years ago, or even before that, when Mars was still a water-rich planet, really, and not that much different than really Earth. Probably a bit colder, but we don't even know that for sure. But it still had probably oceans on it, if not lakes. So it was a habitable environment where life could have originated, I would say, as we don't know how easy it really is, but as easily as on Earth, or comparable to Earth. We should probably say easy, we don't know that about. We don't know that for sure, but as comparable to Earth. And if there was once life there, it would be very difficult to eradicate. I see life basically on the planet, it's like an infestation, if you want so, right? Once life is there, it's very difficult to get it away. And it would retreat to certain niches, habitable niches, where it can hide and still proliferate. We do a lot of work, yes, in the Atacama Desert. I have been several times there, and there's other places like the dry valleys of Antarctica. And we see how life adapts to this environment. It is basically taking the water directly from the relative humidity of the air, because it doesn't rain there. In the driest area of the Atacama, it rains once every 10 years or so. And the same system could work also on Mars, because it can't rain there anymore, but you have relative humidity. It can reach 100% even, that we see on the Viking landers or Phoenix landers, the frost, that shows that there's 100% humidity. And then the microbes that are adapted to this kind of environment basically take the water directly from the atmosphere.
Now, what about, the radiation environment? Because I remember that was one of the big questions about the Viking experiments. Everybody was, saying, well, can you even have surface life in this sort of a thing, even, a few inches below the surface? Where does the habitability of Mars start as far as depth?
Well, we can't give any specific numbers. Yes, radiation environment is harsh. There's no question about it. But it is not as, Mars still has an atmosphere. It's not as harsh as, for example, the moon or so. So if there's a little bit rock layer in between, for example, in salt rocks, we see that within, that are called endoliths, that are microbes that are living within the rocks. And my sense would be, if there's a little bit of cover, like a centimeter of cover, half an inch or something like that, that would be probably already sufficient for organisms or microorganisms that are adapted to this harsh environment on Mars. Mars has also a natural history of about 4.5 billion years. And though you could expect if there's microorganisms, microbes on Mars, that they have adapted to this kind of condition and to this kind of radiation level. We have even on Earth microbes that are very hardy in this respect, like Deinococcus radiodurans, that has been found in the water of nuclear reactors.
Indeed, there were several of those. Another one, gamma tolerance, I think. I mean, just immense ability, just because they can dry out, was my understanding of it, gives them the ability to be able to withstand radiation that's far higher than what you would get on Mars, right?
Yeah, well, there are several tricks about it. You don't even have to try, some don't even dry out, but they have the DNA in form of a ring, and if it's getting split, it itself can put it together, or they have multiple copies of DNA. They have special membranes to protect them. So there's a whole range of ways how microbial life can protect itself from radiation.
And that brings us to panspermia, because could Mars have infected Earth, or Earth infected Mars, just because of these very hardy microorganisms that could survive in space, at least in the radiation environment?
Right. I think that is a distinct possibility. The thing is, it doesn't have to be even a microbe that is so tuned toward to survive a lot of radiation. There's a famous Martian meteorite LH84001, and it is still kind of controversial whether there was fossilized life in it or not. That became very famous when Bill Clinton made this announcement. Then scientific community swung more to the negative and say, yeah, probably don't, there was not fossilized life in it. However, that was, but the interior of this rock, which is the size of a potato, really, was analyzed and it was never heated above 40 degrees C. And of course, if you're within that kind of a rock, you have a protection. Rock protects very well from radiation. So that is a possibility. The rock is more than 4 billion years old. At that time, we don't know whether there was life on Mars, but it was habitable, and it's reasonable to assume that there was life on Mars. And if some asteroid bounces into Mars, rocks are more easily ejected because the gravity of Mars is much less than on Earth. And it would fly mostly in the direction of the sun, which is a big gravity sink. And so Earth is on the way, and some of the rocks are likely to be intersected by Earth. Landing on Earth with a thicker atmosphere, it kind of cushion the fall, or can cushion the fall. So bacteria could survive that trip. The other way it can go as well, that's early Earth life. We know life on Earth probably existed about 4 billion years ago, maybe a little bit more, maybe a little bit less. There's different opinions on it, and it could go the other way too, to Mars, but that is actually more unlikely. More likely is from Mars to Earth than the other way around.
Just sheer size, right? Is the reason it's easier to lift rocks off Mars?
Well, right, because Earth has a much huger gravity and it's more difficult to get it out there. And of course, to land on Mars, Mars has less gravity, so it's again more difficult. And then most of the rocks, if an asteroid hit Earth, they wouldn't fly in the direction of Mars, they would fly in the direction of the sun. So I haven't seen anyone who made a calculation, how likely one is versus the other. But we have right now probably close to 100 Martian meteorites that have been found. So we know that this way goes, I wouldn't say very well, but quite often that way. So it's definitely possible, and we have a lot of evidence that it is like that.
It does actually amaze me to see the Martian meteorites, because we find them in the Sahara Desert all the time. We knew of a few 25, 30 years ago. Now there's 100, and they're everywhere, but we don't see so much from the moon as far as meteorites. So I wonder.
Well, the thing is, though, meteorites are very difficult to recognize. I had so often people coming to me and saying, "Oh, look, I found this meteorite." And then when we looked actually at the mineral composition or the elemental composition, said, "I'm sorry, that is not a meteorite." It is actually quite difficult. And the advantage that we have with Mars, because of Viking, we know the isotopic composition of the atmosphere that Mars has. And if we have this kind of little inclusions, we can pin it directly to Mars. From the moon, of course, we have rocks too for comparison, but we don't have something like this from Venus or so. So that is then more difficult.
Yeah, I wouldn't imagine Venus would be much of a parent body with that thick atmosphere. I mean, how do you get something off, through that?
Right. I mean, if the impact is big enough, you will, but we haven't, there's no confirmed meteorite from Venus that I know of. So I would think that it's very rare, but it is not impossible. And if we talk about panspermia, I think in principle within the inner solar system, that is quite some possibility, but coming something from another solar system is statistically very, very, very unlikely.
Now, Venus is also on the table here. There's, the very upper atmosphere of Venus turns into the most Earth-like environment in the solar system in some respects. Almost as good as Mars if you're up at that, 80-kilometer level. You still have a lot of weird stuff like sulfuric acid and all this business, but it also had that phosphine detection. What was your view on that?
Well, I think Mars still has a more Earth-like environment, but you're correct. There is in the lower atmosphere, about at the 50-kilometer altitude, you have the highest amount of water, which is still very little. You have temperature of 30 to 80 degrees C. The pH is very low. That's actually likely in the minus range. So Earth life can do till about pH 0 if you have a good extremophile. There's a lot of sulfuric acid. So there are a lot of difficulties still for any organisms to get their water. And then you have to think, if you're on a planetary body, you can hide in rocks or something like this. There's not much really to hide. You are free floating in the atmosphere. The phosphine detection, of course, it's intriguing because it is in a kind of environment of Venus. It's considered a biosignature. It is not, for example, if you find it in Jupiter's atmosphere, because that is reducing anoxic, and then you would expect phosphine, but not on Venus. But the amount, of course, is very small. It's in the lower parts per billion. So it is questionable, but I mean, of course, we should check it out. And I did put a hypothesis paper too of possible life in the lower atmosphere. That was about a bit more than 20 years ago. But there we didn't know anything from the phosphine. I said, well, that is kind of a still habitable environment. There could be something. And Venus has an advantage too, that it was in its history, it was different. It could have been that 4 billion, 3 billion years ago, Venus still had a lot of water on its surface. And then it got hotter and hotter. And the organism that originated on the surface then basically retreated to the lower atmosphere because that was our last habitat left. So that is a possibility. And of course, we should check that out too.
And the other thing is that Venus had some strange things going on, like the unknown UV absorber and things like that we just don't know exactly what's going on there with it. That could be, related to life somehow.
Yes, and we picked up on that too. And thought about, if that are, for example, microbes that are covered in, it's called cyclooctasulfur S8. That is a elemental sulfur compound that you can buy in a drugstore. It's nicely yellow. And if they would be coated with that kind of compound, then you would have an UV absorber that could explain it. But of course, there's a lot of inorganic explanations, that it's just some well, it still could be sulfur, but that it's inorganic, just some kind of a dust that does that. But yeah, that is amazing. And also, if you think about that Venus rotates very slowly. Basically, one day is very close to a year. But actually, the upper atmosphere turns around the planet in 3 days. I mean, the lower atmosphere, whereas 50 kilometers and up. So if you have microorganisms, in principle, they could do photosynthesis. So that is still a possibility.
Now, back to Mars. Now, It seems that Mars, if there's life there, and some of your papers get into this, is that you're going to need briny water. You're going to need salt. What is the salt profile on Mars? I mean, does it look like it's got sufficient access to salt subsurface to have that briny mixture?
Well, the orbiters show that there's a lot of salt on Mars. We have, for example, the Southern Highlands. There's a lot of sodium chloride. And we have a lot of sulfur salts where the rovers were. We also seem to have chlorate and perchlorates. Those salts are better that you in that way that you can go to lower temperature and keep the water still liquid, but they are more harmful or more challenging for microbes. So easy one is, of course, sodium chloride. And we have on Earth, if you think about Salt Lake in Utah or so, even if you have a saturated sodium chloride brine, you still have microbes inside. The key, I think, is to have hygroscopic compounds. So hygroscopic compounds is those that can extract water directly from the atmosphere. If you think about it, if you have breakfast and you have a salt dispenser, right? You have usually salt in, and then you have rice grains in it as well. And the rice grains are in it because they are more hygroscopic than the salt. So the rice grains suck up the water and the salt stays dry. That's what you want with the salt container. But if you take the salt out on the kitchen table, for example, it will become wet and clumpy because it attracts water from the atmosphere. And this kind of principle microbes use in very dry areas. And if the compound is so hygroscopic that it becomes liquid, that you actually become a brine, then this is called the liquescence. So then you can even get more water that way.
It's amazing how salt is used in biology. I mean, that's how, the human body moves water in one way,
Yeah.
Which is why when one perspires, it's salty. It's because it's, that's what starts it.
Right. And if you think about it, our blood is a compound that is most similar to it is salt water, basically.
Yeah, we walk around with the ocean. We carry the ocean around with us still to this day.
Right.
Now, where on Mars is the favorite place to look? So say we want to go and do direct life finder experiments again. Where do you think the best places to go are?
Well, I mean, there's several colleagues have different opinions on it too. And my favorite one would be to look where the salt rocks are, because that way the microbes can get the water. And it would also explain the Viking experiment, because we can talk about this a little bit later, because I think some of the results could be interpreted that we accidentally killed microbes that use that principle to get water from the atmosphere. Because we put too much water on it, we essentially drowned them. There are other spots too, which will be very much worth to look at. For example, lava tube caves, I think, would be a great location too. And there are ice caves and that exist on Mars, or we think exist on Mars. But of course, it's difficult to get into the caves and with a rover. And then we could look into subsurface, or where you have liquid water inclusions in ice, we can look there too. But for all of them, we have to go relatively deep. So my favorite spot and the easiest accessible are actually salt rocks.
What of subsurface lakes? Antarctica has subsurface lakes, pressure lakes that seem to teem with life as far as we can tell. I mean, there's not a lot of great work done there, but some of it seems to show that these are habitats for biology, even though they're, it's very, very cold, high pressure water down there, but still, well, these lakes were sealed. Could that be happening with Mars? And I know that there's been recent work that says that maybe there is evidence of subsurface or subglacial lakes on Mars. Would this be a place to go?
In principle, yes, it could be. I mean, it's those lakes have been found with radar, or let's say we think about it because we cannot directly observe it. But based on the temperature profile and what we know from these locations, they would be highly concentrated perchlorate brines. if we do have that, because those, if you have, for example, magnesium perchlorate, that can still stay liquid at minus 70 degrees C. The sodium perchlorate prime is quite a bit less. These microbes can take better. But those liquids with so much perchlorate are very challenging due to the nature of this kind of salts. So whether we find their life or not, it's difficult to say. I'm kind of skeptical, actually, because my research group does a lot of work with salt extremophiles, also exposing to perchlorate, to chlorate, the sodium chloride concentrations. We work with water from the Don Juan pond where there's a lot of magnesium chloride. And the stretch of what at least Earth microbes can do, and the best one is actually a yeast that we tested, to what would be required for the subsurface Martian lakes. There's a big canyon in between. Whether that can be overcome, I'm skeptical, but we don't know. I mean, if microbes all the time are exposed to it, they develop adaptations to it. And whether they can adapt to so much perchlorate, we simply don't know.
It always seems to come back to perchlorates on Mars, because that's also the big problem with growing crops there. Should somebody ever found a Mars colony, is to, you have to wash those things out.
Right.
And, now with regards to the future, so we were briefly talking, and we're going to talk a little bit more deeply about the Viking experiments and their intriguing results and how we might have actually poisoned them with the water, which I found that paper to be really interesting because I hadn't thought of that before. I was like, well, if you're adapted to relative humidity, you can drown easily. And I hadn't thought of that angle. But what do you think of the overall Viking experiments? Do you think that the intriguing and controversial and weird results should be repeated? Should we come up with a better experiment and do another in situ life-finding experiment on Mars?
I mean, the Viking experiments were done in the late 70s and still in the beginning 80s. This is now 50 years ago, nearly 50 years ago. I mean, for the time, they were very good designs. And the idea was simply that water essential for life on Earth. The investigators thought that would be also on Mars that way. And at that time, people still thought that maybe Mars has a global biosphere. That was still a view that was entertained. And we didn't really know too much on the environmental conditions on Mars. And there you could argue, okay, those life detection experiments were probably conducted a little bit too early before we knew about the environmental conditions. Now, there has been a study in the Atacama Desert, for example, not from us, but some other investigator, Azua Bustos, and they found that after there was actually a big rain in the driest area, in the Yungay area, and that 80% of the indigenous microbes died because, if you're all the time adapted to just take water from the relative humidity in very small amounts, and then you pour water over it, it's like you're essentially drowning. In scientific terms, it would be hyperhydration or drowning. But it's nothing else. If an alien flies by and sees you, oh, look, this poor human is thirsty in the desert, grabs you and puts you in the middle of the ocean, right? That is essentially what we did during Viking. So, and that would be also explaining some of the confusing results at the time. And it just came to be that it was explained as inconclusive or even negative, because at that point, when the interpretation was made in the early 80s or mid 80s, we thought there were no organic compounds on Mars. And there's a gas chromatograph mass spec measurements indicated 2 trace amounts of organics, but they were interpreted away as contamination. And then Jeffrey Soffen, the project scientist, was saying, well, no bodies, no life, right? If you don't have any organics, how can you have life? But now we know that, well, the trace organics that Viking detected were actually indigenous, or most likely indigenous. And the Phoenix mission, the Curiosity rover, and the Perseverance rover all found organic compounds now. So the interpretation should be now quite different.
Actually, that's very true. I remember at the time that they were blaming those trace detections on cleaning fluid.
Yeah.
If you recall it, they said it was leftover cleaning fluid. No, it wasn't.
Yeah.
And now, obviously, we've since found plenty of organics on Mars. So it just goes to show you how interpretation can change.
Yeah. And the trace compounds were chlorinated compounds that perfectly fit to Mars.
Yep. Yeah, as far as we know now.
Yeah.
So what could we do to go back and re-examine the Viking results and try to come up with a different new interpretation of them?
Well, I mean, one thing what was never done, which if you want to do something like Viking again, was with a labeled release experiment which showed Gil Levin and Patricia Strutt always said that it's like it detected life and they detected metabolism. And in the big picture, it did show it, but there were some problems with interpretation as well. This one thing what they did not do was using both chiralities of the amino acids or of the compounds that the microbes supposedly metabolized, because it was kind of a mix. And so the explanation was very different because look, on Earth, we basically use the same handedness of amino acids or the same handedness of sugars too. So if they have the same handedness as the one on Earth, we can say, well, that's only those ones were taken up. Then we can say, well, it's either Earth life or it is Mars life that by coincidence has the same handedness. If I take the other handedness that is not on Earth, we can say, okay, it's Martian life and it's independent in its origin from Earth because it developed the other handedness. And if the amino acids taken up at about 50% levels, we can say, well, that's chemistry. That's not life. So that would be nice. And actually, it was planned to analyze for that, but that probe that went then to Mars crashed into Mars. So that was lost. Nowadays, if you would make it over, we probably would send different life detection experiments to Mars because we have much better technology. We have a lot of things on the chip. You know, we have basically a DNA sequencer on the chip. We have to be careful, of course, because Martian life not necessarily would have to use DNA. My work group also used motility, the natural movement pattern of microbes, and compares that to Brownian motion, also the random movement of other particles. And with that, we can indicate whether something is biological. And there's a lot of other great ideas. And I think we could put a really great life detection mission together to send it to Mars.
What is it about chirality why did life on this planet favor only one, but not the other? You know, we never see the other, and that would be definitive, as you say. But the thing is there something there that might force that chirality on life?
Well, what it forces that you have to deal with macromolecules. So the molecules are really quite big. And they then have a certain kind of image or mirror images that the mirror image doesn't fit then. Because you have all those macromolecules have to tightly fit into each other, for example, to build proteins or something like that. And if you have ones of different handedness, they don't fit into each other. So life had to decide relatively early on one-handedness. And then all went with this kind of handedness. We have to be a little bit careful because there are some tiny exceptions to it. Like, you know, life is messy, I guess. But for 99% of the cases, this is the handedness that works.
Given what you know about microbiology, and this will get into interdisciplinary stuff, we're talking about chemistry and all this stuff, and how could astrobiology be improved by getting as many different scientists from as many different disciplines as possible weighing in? I wanted to ask about that, but I also wanted to ask about, do you feel, and it's a point blank question, as one of the prominent people in astrobiology, does this universe teem with microbial life?
Well, I think likely, but we do not have a certain answer. Look, there's two components to it, the origin of life and the persistence of life. The persistence of life is really no problem because life has so many tools, is so adaptive and can adapt to a lot of different kind of environments, a lot of different kind of conditions. Not everything, but really huge, a huge breadth. The origin of life is a very difficult question. And sometimes I feel pathetic about us that we still don't know how life originated on our planet or how all came together. There's two viewpoints from that. One is that life originated basically as soon as life could originate on this planet, from what we know. So you would think, okay, shouldn't be that difficult, right? On the other hand, I think it's a problem because you have to get something together what builds a nice membrane, because otherwise, you get an equilibrium and death, that you have an enclosure, like for the first cell. You need something that produces energy, that proteins do this nowadays, but maybe you can get away with peptides or something like that early on. And then you need something for reproducing. There's nucleotides and DNA, RNA for us. So, but you have all of the three components come together and actually working together as a unit in a short time frame and in a very close location. So for me, is that a problem of infinite over infinite? So there is that this happens from my biological, physical, chemical understanding would be like 1 over infinity. But then just on our planet, you have infinitive small habitats and location where this can happen. So if you have infinity over infinity, anything can be the result. Anything from it's definitely at least 1 because we are here to again infinity.
That isn't said enough because all right, let's just play with the RNA world for a minute. Well, okay, but what happens if you have untold trillions of strands of useless RNA? Your chances of having a good piece are raised. So so the more chances, it's more lottery tickets. And in a let's say it happened in a reducing pond, like in Kamchatka or something like that. I believe there was a scientist that did work on that.
Right.
And cell walls started appearing and things like that. If you have millions and billions and trillions of chances, then is it that surprising that over a couple 100,000 years something will happen?
Well, but we don't know how it happened. If it's that easy, why don't we know how it happens? I mean, an RNA by itself, yeah, it's a great molecule, but it is not life. And, I see it too, like you have those nucleotides swirling around, you have this chains of amino acids, proteins swirling around, and the membranes. And in each of them are really, if you think about dumb molecules, how it comes that they work together. I'm not saying here that the origin of life is very unlikely. I just say, okay, we really don't know. I mean, from my personal feeling or so, I have a very difficult time to really believe, okay, we are the only one. That would kind of blow away. That would be really scary if that would be the case.
Oh, that would be.
So I don't really
Yeah.
think that either. But we have to acknowledge that we simply don't know.
The thing is that we also have an elephant in the room, so to speak, which is the sun's birth cluster. Because when life appears here, it was still relatively in that, and that panspermic effect could be passed from a different star system that happened to be passing close by. So we have that too, that maybe none of it started here and it was transferred from another star system entirely.
Right. I would doubt it that it was transferred from another star system by random, impacts or anything like this. But there's this interesting paper by Francis Crick and Leslie Orgel of directed panspermia, that there was a kind of alien civilization that basically seeded Earth. Was kind of interesting because I had this at a conference in Beijing, I walked with Leslie Orgel, who was at that time still alive, and I asked him, you know, how Francis and you came up with a directed panspermia. Was that because you got frustrated because, you know, the origin of life is such a difficult problem and you don't get any further? And he sounded a little bit pissed there and say, well, you know, Francis could publish anything once he got his Nobel laureate there. And then he said, no, that was only a joke. And I said, well, it is not a joke. I mean, it does make certain sense, you know, it's logical reasoning. But he didn't want to have it, you know, talking about that. But I think, you know, again, that is something what we a priori cannot exclude. It's a possibility. I mean, you mentioned before that we are basically saltwater bags running around, right? This would more point to that we actually originated on Earth because there was salt water to start with, but again, we don't know.
But there are a couple of aspects to this. Directed panspermia being scary because if you, there have been suggestions, and I don't know how good this is, and maybe you can answer the question, but there have been suggestions of searching the human genome or the genomes of Earth in general for artificiality, you know, genetic SETI.
Yeah.
What's your view on that?
You know, all research, I think, in that way is free. Yeah, go ahead and look for it. As far as I know, nothing has been found on it. There's one other reason why I wouldn't necessarily exclude it either as a possibility that this happened, because if you think about it, I mean, if we now know of more than 5,000 exoplanets. As soon as we identify a habitable planet, we could put a rocket together. We could put some petri dishes inside, put some microorganisms there dormantly inside that can stay there for maybe even millions of years, and have some ejection system that once the rocket gets there, ejects there, and they're going down on a parachute or similar to that into the ocean and settle this world. Whether we should do it or whether it's ethically the correct way to do it, I don't know. This is to be discussed. But I mean, if aliens did it, it could be the case. Yeah.
They may work on different rules and see nothing wrong with it. You know, they may have just
Yeah.
said, you know,
Well, I mean, you know, if, of course, we wouldn't know from such a distance, but if there is no previous life on that planet, I don't see anything wrong with it either, because life wants to spread out. And if we put then our microbes there, and evolution will go its way, and after a few billion years, we have the complex life and maybe even intelligent life. I think the ethical problem would come in if there's already some other life there.
that's going to be the big question with Mars because, like it or not, we have multiple plans to go there and put humans there, possibly before we know if anything is there, anything might be left. And I hold the same view in that if it's a lifeless rock, let's colonize it and expand the human future into space. But if you find an indigenous form of life, you need to leave it alone. And I worry that we might be moving a little bit too fast as far as going to Mars potentially. I'm not sure that I'm completely sold we will be able to do this as easily as some say, but what's your view on that?
I think that if there's indigenous life on Mars, then we have to do everything to protect it. Whether it means not to go there at all, I'm not quite sure. It depends. We have to find out more, I would say, because Mars is a very harsh planet. So life is not, there's no global biosphere there. I think so far that we probably can be for sure. If there's life, for example, in lava tube caves and maybe in the salt rocks, I think it would be probably still okay if we are carefully treading and putting a station somewhere where no contamination will happen for this Martian life or where there's no interference. I guess I'm not so concerned because I think any kind of Martian life will be still better adapted to Martian conditions than any Earth life because they have so much time to adapt to it that I think that would be quite safe. But still, we do not want to interfere with it. If there's life, even if it's microbial life, I would then, if you want to have a station or a research station or so, again, we have to be careful, put it in a location where it doesn't interact with indigenous life.
Probably not all that difficult as long as you keep it away from the salty subsurface water. But my question for you, though, is okay, yeah, Mars has been sneezing on Earth for its entire existence, but is there the possibility, can biology go as far as to be a very generalized pathogen in a dying planet like that that might pose some kind of a danger to life on Earth if it's not ready for it?
From our biological understanding, it cannot, because there's always co-evolution of host and pathogen. So those pathogens that you have on your body right now, on any one of us, they co-evolve with a human being. And this is for all animals and plant species, the same thing. So if you have, for example, a microorganism from Mars that comes on Earth, it would not be adapted to humans, would not be adapted to any kind of complex life form on our planet. However, you have to consider this also with a grain of salt to speak to, because there could be still toxic interaction. It would not be a pathogen that could infect you with flu or something like that, but there could be still, if, they come over here and they are dying or do some kind of strange metabolism, release some toxic compounds that could be harmful for us or other organisms.
The reason I bring that up is the one thing that we seem to be lacking, which is a second abiogenesis of life on Earth. And the answer to that may simply just be that it gets eaten.
Right.
So if abiogenesis is still happening, it gets eaten. But what if the Mars stuff is better at eating than our life is? And that's what worries me.
Well, I think it's the same thing. It's that any kind of Martian organism, maybe the Martian organism would still do okay in the Atacama Desert, in the driest area there. But otherwise, if it falls into the ocean, it just drowns. If it is somewhere else, it will be eaten by the Earth organisms. Because the Earth organisms, there are so many, there's so much diversity, they are way better adapted to Earth than any kind of Mars organism. The other reason why I'm sure is because we have so many Martian meteorites. If that would be not so, we probably would be taken over by Martian organisms by now.
True. It's been, as I said, it's been sneezing on Earth this whole time. And thankfully it is, because the Martian meteorites are rather interesting, just geologically, because it represents almost extinct volcanism, not unlike Earth. And it's almost like Mars is a frozen time capsule geologically. And it's just fascinating for that reason, above and beyond, the possibility of also having had an abiogenesis event.
Yeah. Well, the volcanic activity really decreased with time on Mars. But I think it could be still that you have, even nowadays, some volcanic activity. I mean, we don't see anything now. But I know I read a paper that was implicated. There was a lava flow that was about 1 million years old. And on a geological timescale, that is really not much. So from that perspective, it still could happen, but probably nothing major, yeah.
Still, though, it's interesting. It's interesting. Now, let's move to yet another body in the solar system, Europa.
Mm-hmm.
What is your views on Europa as a potential life target? Could it be even better than Mars?
Again, we would refer to the origin of life and the perseverance of life. With Europa, the ocean underneath could be a great habitat. We don't really know about it because we didn't have a chance to probe it. The ice layer is thought in some areas several kilometers thick. In some areas, in the Chaos region, for example, probably much thinner. But unfortunately, we never had a mission. I was at some point in a science definition group. We wanted to have a basketball-sized lander to look actually and sample the ice, but that never went any further than that. So in principle, it could be a habitat. We do have a crusty mantle with rocks. So we could have something like the hydrothermal vents on Earth, the black smokers or something like that. So that would be encouraging. Now, the question is again now with the origin of life, right? And a little bit the problem is that we don't even know the location of the origin of life on Earth. If, like quite a few of my colleagues believe, life originated on Earth at the hydrothermal vents, then this is a distinct possibility on Europa as well, and a good possibility that we find life there. If, however, which I tend to more, that life originated close to the planetary surface on Earth in a Darwin's little pool, or if you want to call it, or I actually favor even more a tidal flat environment, because you have the cyclings of drying and wetting, temperature difference, and you could have a tidal flat too, where you have some hydrothermal water. If you need a planetary surface for that, then you probably do not have any life in Europa's ocean, and it's just water or water with some salt. Unless there is a way that life also can originate at hydrothermal vents, only even if it's originated on the planetary surface on our planet, doesn't mean that it cannot under other circumstances originate. So from that, it is definitely interesting body. It could have life on it, and that is something too what we should try to find out. We could even, that is probably also the only body in the solar system other than us, where we could find maybe a little bit more complex life or multicellular life. Nothing too complex, but that life evolved toward multicellular life, which we have at the hydrothermal vents on Earth as well.
That's interesting, because throughout this entire conversation, we have not talked about macrofauna at all. We have only talked about microbial life. Do you expect that Mars only could have produced very, very simple prokaryotic type, the very beginnings of life, and stuck there? And then we were just talking about with Europa, maybe it might have multicellular, sludge or something like that. So, I mean, could Mars have gone any further in its history than a single-celled, simple life?
Yeah, this is kind of an interesting question, because I wrote in one of my books, I think it was Cosmic Zoo, Complex Life on Many Worlds, I suggested that on Mars there could be nematodes still, so simple worms that we find even in Antarctica or so. And one of the reviewers, who I knew very well, wrote on the site, "Come on, Dirk, do you really believe that?" So the thing is, evolutionary time scales are very difficult to judge. But one thing what we know, if there's a lot of evolutionary push, well, a lot of organisms getting extinct, but it also creates new possibility, new opportunities, and evolution marches much faster. So personally, I could still imagine that you would have on Mars something like nematodes or so, something simple multicellular life in certain very distinct habitats, but not more than that.
But in the past, I mean, could we find a fossil? Some kind of a clam or something on. I mean, we haven't so far, but I mean, is that possible on that planet?
Well, that's like, we do not want to exclude any possibility a priori. That's, we are too focused on something, and suddenly there is something and say, no, that can't be, and then we overlook it. So regarding a clam is actually already kind of a complex organism in a way. So I would not think so, but of course I cannot completely exclude it either. What has been found, or some people claim, and it actually looks a little bit like this, to find this kind of stromatolites that are microbial colonies that then fossilize as rocks. And some of them actually do look like, very similar to the stromatolites on Earth. So this would be a distinct possibility, but these are still, even if they live in colonies, they're still microbial cells. But like I said, I mean, I wouldn't exclude simple multicellular life totally. I think it's unlikely, but it's still a possibility.
Even though the stromatolites, and I've seen the same pictures, and they do sort of resemble that, but they're also billions and billions of years old on Mars, so there's a lot of age there. But at the same time, geologically speaking, there is so much evidence of water on that planet in the past that, I mean, hematite and all sorts of just evidence everywhere of long-term water. And I guess that is the first step, right? Is that Mars had to be wet for a very long time, which comparatively, let's say, what was it, probably hundreds of millions of years. But the thing is that with life showing up on Earth very quickly, and Mars having held water for geologically significant amounts of time, there's the formula, right? I mean, that's the basics.
In principle, you're correct. However, why we are so skeptical about this, I think mostly is because, I mean, look, there's so much biodiversity on our planet. Life originated on our planet about 4 billion years ago. But the first multicellular life is probably about 1 billion years old. So we had basically 3 billion years of where there was only microbes. And even 1 billion years ago, there was the first sponges and stuff like this. So really the first really kind of multicellular life, what we mostly envision also, it's about 600 million years ago with the Ediacaran fauna. And this is on a planet that has so much biology. So Mars, of course, was much more difficult in that way, that there was probably for a long time certain habitats, still lakes or puddles or wherever. I think I have a lot of colleagues, and I do believe too that about 4.2 billion years ago, we likely had microbial life on Mars. But on Earth, it took 3 billion years, and that would have to be really, really fast to get to the multicellular stage, given the planetary conditions as well. So we don't want to exclude it again, but from the first look of it, it doesn't look like that.
So the very famous Miller-Urey experiments that showed that the building blocks of life can come out of a test tube. And that was what, the 1960s. And here we are many decades later. Do you expect that we will come around from a different angle and show that life is common in the universe simply by a microbe popping out of the test tube of the scientist? And that tells us it's either easy or it isn't.
Well, the Miller-Urey experiment is, you say, the building blocks of life. They only found amino acids. And they actually didn't use the right gas composition of early Earth. They used way more methane, where you have more amino acids building. But it was only amino acids. We don't have life with that. And we find a lot of amino acids in interstellar space too with the telescopes. That didn't bring us, it's a famous experiment, but it didn't really bring us any further in the main question. It gave us a little bit more understanding, maybe how to look and so. Right now, someone to find, makes the right mixture, and then you actually have a complete new cell or a life form coming out of the test tube, seems to be very, very far-fetched, I must say.
It could be, but the planet did it.
Yeah, well, the planet was very big and microbes are very small. You basically have infinite possibilities. And you had, even so we think it happened relatively quicker, but you had probably 100 million years. I don't think any one of us gets that old.
Though, it seems strange to me that actually is stretching back into the late heavy bombardment. Earth was not that nice during that period.
Yeah.
And yet it happened somehow. And that's quite the mystery.
That's true. I mean, the late heavy bombardment has been criticized whether it existed at all, that it was more continuous bombardment. But the latest implication from the scientific literature point actually that life was already on our planet 4.1 or 4.2 billion years ago. That was definitely, even if the late heavy bombardment happened, before the late heavy bombardment. And life just survived that kind of bombardment. Maybe at the hydrothermal vents, maybe on the subsurface.
Some sort of, lucky circumstance, but maybe not so lucky because Mars was undergoing this as well at the time. So it was getting hit as well and had volcanoes, had water, had hot springs. Don't know if it had hydrothermal vents. Probably, I would guess, though. Wouldn't you think?
Yeah, I would think so probably too. But Mars was not hit as badly, and this is simply because Earth is bigger. And then the thing you have to keep in mind too, that near collision or the bumped together with a planetoid, Theia, that basically created the moon. And then we had for quite a while a lava ocean basically on the surface of our planet. So Mars didn't have that, so it's probably there were habitable conditions quite a bit earlier on Mars than on Earth.
I hadn't thought about that. The Theia collision with Earth delayed its habitability compared to Mars. No idea.
Right. And putting the loop back, what you at the very beginning suggested that life may come from Mars, right? That would be an indication too that it could be actually that way. Because on Mars, life would have to have more time to evolve.
So, how would we tell genetically which came first, the chicken or the egg, so to speak, or Earth or Mars? Could we tell that from the genome of anything we might find at Mars?
Well, we might be able to because the DNA tree on Earth is very well developed. And if we find no Martian life, and if it's related to Earth life, it probably works with DNA too, unless it would be very, very early on. But let's assume for a moment it's DNA too, and we probably can stick it on the tree of life, probably pretty close to the root. And then we have some kind of an idea, can have some insight what may have been first.
It's going to be fascinating to if we glean any clues. Last questions for you involve much, much greater things. Big, giant alien civilizations and technosignatures and biosignatures on exoplanets. How are we positioned to look? I mean, we know about technosignatures because we have SETI, but how are we positioned with JWST to look for biosignatures? Do you think we could see a planet that has a biosphere with that telescope?
Unfortunately, I don't think, not conclusively. Look, tell my students always, if you do astrobiology, you have to get close and personal. And to look something from the far distance, it's very difficult. Maybe we can detect certain gases, maybe even mixtures of gases. But is that really then caused by life? That will be very much discussed. But this is not then evidence because we can probably come always up with abiotic explanations. The only thing what I would say could sway me in that if I would find massive amounts of chlorophyll, for example, and can screen for that. I don't think JWST is able to do that, even if it's there. But if we can see that, then that would be very difficult to explain, to see those massive amounts of that kind of complex molecule, which we wouldn't expect to form abiotically, at least not at this large amounts. But see, biology again is this kind of messy because first of all, there are different chlorophylls on Earth. You know, there's bacterial chlorophyll. Then even some plants use different kind of chlorophylls at different wavelengths. And then there's also photosynthetic organisms that use carotene or rhodopsin for light harvest. So even if we have an alien biosphere and it does photosynthesis, doesn't mean that it actually uses chlorophyll. It could use something else too. But still, if I would found this huge amounts of it, then I can say, okay, there is likely a biosphere. But otherwise, I don't see really right now anything else what I would say, okay, with what we can do right now with our technology, looking at exoplanets, where I can say, okay, I agree that is a signature of life.
Now, how does that relate, the detection of chlorophyll? I mean, can you directly detect chlorophyll, or is this just related to the vegetative red edge?
What we usually see is a vegetative red edge, yes. Whereby this is then kind of, it becomes a kind of a little bit dicey too, because it can be located at different wavelengths too, depending what kind of chlorophyll is used. Yes, but you're right. It would be the red edge, basically.
Now, could it be possible that alien plant analogs just don't have that structure to, reflect infrared like that?
Well, obviously that could be the way too. We can think of very different ways how light energy can be taken up, how chemical energy can be taken up. Well, if you think about it, maybe those organisms over there using magnetic energy. or they use osmotic gradients for energy harvest. So it doesn't have to be or thermal gradients, the thermal capacity. So it doesn't mean that only because on Earth we use chemistry and light energy for life forms to be powered, that it has to be on an alien planet the same.
Now, my last question is envisioning alien planets, since we're on the subject, different color stars, because, the sun has its spectrum.
Right.
But yeah, we also have type K and, type M and maybe even type F. And they're probably going to change the colors of the vegetation, wouldn't you think? What is the current thinking on might not be so green there?
Well, actually, I had a smart PhD student who just finished. And what she did, she used garden cress and did it under normal solar illumination and the illumination simulated from a K-star. And what we found out is actually not only garden cress, but also cyanobacteria. And I don't know which one was now. One of them was basically equal, was as happy with the K-star light as with the G-star from our sun. And the other one, I think it was the cyanobacteria, actually grew better with the K-star illumination. So that shows you already, actually, life they are very adaptable. Of course, all of them were green because, that's they're Earth organisms. But yeah, there can be different color.
It does get you wondering, though, that type K looks really nice as far as a habitable star, and they're even more numerous than the sun, and that our sun might actually have been rather precarious as a life-supporting star, and that K might be better. And that gets into the question of super habitability, which I will ask you next time if you will come back and visit us when we will get into that question.
Okay, I'm happy to do so. Happy to be on again here with you.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.